Okay, so I'm going to be making a video about ammonia decomposition today. Ammonia decomposition as a solution to hydrogen storage issues faced by conventional high pressure systems such as 350 or 700 bar carbon fiber tanks. Ammonia serves as an intermediate solution to um, enabling the deployment of hydrogen fuel cell vehicles, but without facing the constraints imposed by the infrastructure required to dispense the high pressure hydrogen fuel, to compress the fuel, to compress the gas, and to store it on board the vehicle via these very heavy composite cylinders. So I've compiled a number of screenshots about ammonia decomposition technology, and I will be going through some of those and discussing it. So starting off, we should first identify what the optimum catalyst is. Now, in this section of screenshots that I'm displaying, these are actually about hydrazine, which is a separate topic. Obviously, I do think hydrazine is an attractive option. So right now we're going to be talking about ammonia. So there's been some research on using ammonia as a transportation fuel, and that research tends to come to the same conclusion, that despite the fact of that ammonia is caustic, it's not actually toxic. That's different. It's caustic, so it does pose risks to operators, but those can be mitigated with proper handling technology. Ammonia appears less dangerous to human health than hydrogen. Right? That's not a conclusion I came to. That's a conclusion that that multiple researchers came to when studying ammonia for transportation use. So this conclusion came to the same conclusion that I did, which is ammonia has a lower risk than propane. I went through the lists of industrial accidents at OSHA and found per capita, essentially, per ton of material handled, I think we were using like 40 million tons of propane or something. The number might be totally off. I don't remember. I went through the list of accidents since OSHA compiled the first accidents, and I found the per capita rate per ton of material handled, the number of fatalities is higher for propane than for ammonia. It's actually, in fact, significantly higher. Okay. So here you have accidents for hydrogen and accidents for NH3 and then fatalities, right? So this is the same conclusion that I came to. Right, so smaller quantities of hydrogen handled than ammonia, significantly smaller quantities. It's not understandable why hydrogen as a fuel is widely promoted, whereas ammonia is presently not considered at all. It's just unknown. It's not considered. If you're in the low emission mobility community, where they're talking about fuel cells or batteries, whatever, alternatives to carbon-based fuels, you're always going to hear high pressure hydrogen for PEM fuel cells, and you're going to hear batteries. You're never going to hear anything else. When there exist a considerable number of alternative options, it may in fact be more attractive. Okay, so again, we've gone over that. That's basically the number of accidents. I would recommend that you go to OSHA, and the reason I used propane is because I was not able to get numbers for hydrogen because it was including hydrogen sulfide. It was difficult for me to exclude hydrogen sulfide accidents. Most of the accidents, if you put hydrogen in OSHA, you get hydrogen sulfide accidents. Whereas anhydrous ammonia, it includes only anhydrous ammonia. Now, but propane, of course, it includes only propane accidents, and propane is going to be similar to hydrogen, although arguably safer because the minimum ignition energy is a lot higher. So it's easier to ignite hydrogen, as we all know. Okay. So what would an ammonia tank look like? Well, an ammonia tank doesn't need the carbon liner to withstand the high pressure. So it's not for structural reasons. This liner here, you're seeing, you might think, oh, this is a carbon liner like a composite cylinder for hydrogen. In fact, it's an ultra-high molecular weight polyethylene liner, which is meant to provide puncture resistance. So this is an idea that I came up with. I have a relatively thin aluminum tank providing the structure, and of course, as ultra high molecular weight polyethylene or polyethylene in general doesn't have any compressive strength. It simply provides impact resistance. So its fracture strength is very high, order of magnitude higher than carbon fiber. So it's used for ballistics. It can withstand a projectile impact. If you lined an aluminum or titanium or some kind of metal tank or even carbon fiber tank with a ultra high molecular weight polyethylene liner, you'd have ammonia tanks that are puncture resistant that would be very unlikely to release ammonia in the event of an accident or collision. Okay. And this box is actually the cracker, and this is the scale. This is based on the available data regarding microchannel ammonia crack, and that's what we're going to go into very soon. Is the science of ammonia crackers. Okay. So again, I'm just going through these. I'm very prolific in compiling screenshots of important data. And it's always very useful. Here you can see the price of ammonia in Hungary, very, very inexpensive. Right now you say, well, this is gray ammonia, right? It's made from natural gas. Yes, true. There's no reason to think that green hydrogen couldn't be relatively close to the price of SMR, steam methane reforming. Okay. Here's an example here about the safety risk of hydrogen. 50,000 cubic feet of hydrogen is the chemical explosive equivalent to 5,800 pounds of TNT. Right? So it's by no means safe. So when you have all these people promoting fuel cell electric vehicles with high pressure dispensing systems, that's what we're going to go into next. I recall that I compiled some data regarding accidents involving high pressure dispensers in Japan. In fact, in Japan, they require trained personnel to operate the dispensers to fill these fuel cell vehicles. They don't let consumers use them. They experienced a number of accidents in Japan with CNG systems. In fact, Pakistan is known to use a lot of CNG. And if you put CNG accents in the search engine, you'll get a lot of results in Pakistan. CNG has not had a stellar record. And I'm not being biased against these high pressure chemical flammable gas systems, right? Because that's what we're comparing. We're comparing basically, I mean, ammonia is flammable, but it's very hard to ignite. So we're comparing a hazardous non-flammable chemical to a highly flammable chemical gas. They're both gases. So here's an example of the cost of high-pressure dispensers. Very high cost for these systems. This is for this is a small fueling container system, a fueling system that's meant to fit in a container. Cost is $10 a kilogram. I read in the Department of Energy report $12 a kilogram right now for the total round-trip cost. By the time it gets from the hydrogen plant to the dispenser, the reason for that high cost is just takes shipping, for example, right? Because the density of hydrogen is so low, if you're going to ship whatever amount of hydrogen, right, you're going to spend the same amount of money on that semi-truck. But if you're carrying 1,000 kilograms of hydrogen as opposed to 8,000 kilograms of ammonia, that cost is going to be proportional to the storage density. So it's much more expensive to transport hydrogen, and transportation is not even the largest cost contributor. Compression is expensive. These large diaphragm compressors are very expensive. In fact, I'm going to go through that as well. You have to deal with embrittlement in the compressor. You have to deal with embrittlement in the dispensing nozzle. All of these components that are going to be used to transport hydrogen and store hydrogen are going to face embrittlement issues. Some people say, well, ammonia is toxic. Corrosive, excuse me. Ammonia is not corrosive to most metals. So that's storage of ammonia is not a challenge the way it is with hydrogen. Okay. So these are the cost estimates for the hydrogen fueling stations. And there's a lot of unrelated screenshots here for us that we can ignore. So here is the cracker specifications. Okay, so the example of a nickel microfibrous cracker, and here you have the reaction temperature and the residue. So if we assume a feed rate of 150, we go to where it's 650, we have 5 parts per million. And now, of course, 5 parts per million is in excess of what is tolerable by a PEM fuel cell. PEM fuel cells, ideally, you want to be below 100 parts per billion. We can reduce that 5 parts per million to 100 parts per billion using an absorbent, using a carbon-based absorbent. And in fact, if we go to okay. All right, so what about catalyst stability? This is important. So no deterioration for 110 hours. I have data showing that for a ruthenium microchannel reactor, they ran it for 900 hours and they found minimal deactivation. So the zeolite absorbent, that's the key, and we're going to go over that in a moment. Okay, H2N2 selectivity. That's something that we want to discuss as well, because when you decompose ammonia, you get nitrogen and hydrogen gas. Now, nitrogen will reduce the efficiency of the fuel cell. If we have nitrogen in our feed gas, it actually reduces the both power output and efficiency of the fuel cell significantly. So we want to remove as much nitrogen, and to do that, we can use what are called membrane separators, polymeric membrane separators, as pictured here. All right, so here we have varying levels of selectivity, right? The previous number was much higher, but regardless, it's very easy to separate nitrogen from hydrogen because of the difference in the molecule size. I know that hydrogen is 120 ppm. I don't know what nitrogen is, but it's almost double that. Okay, so here's an example of a paper discussing the issue of a fuel cell running on reformed gas, nitrogen containing hydrogen. Okay. So here they found that it's not so much of an issue running with nitrogen, but the other paper I found showed that it did have a significant effect. So of course carbon monoxide is what you're most concerned about. So these are the purity requirements for the PM fuel cell NH3. So 0.1, that's going to be 100 parts per billion. So ruthenium is the most active catalyst by far. And so before we start discussing catalysts, I want to just state that there's a plethora of catalysts that are considered. Okay, just a wide range of catalysts. What they all have in common is they have low rates of reaction. They have low reactivity until they reach high temperatures. With ruthenium, you get much higher conversion rates, much higher reactivity at lower temperatures. That's the main difference. All these catalysts can decompose ammonia at high temperatures above 700 degrees Celsius. For example, nickel is very active at those high temperatures, as we previously demonstrated. But we want to minimize our energy consumption for the cracker because, of course, cracking, unless we have a source of heat, unless we're running an internal combustion engine, we're utilizing the exhaust gas. If we don't have that source of heat, we need to provide heat on board. We need to combust a small amount of hydrogen to provide that heat. And it's actually not such a small amount of hydrogen. It amounts to about 20% of the total fuel flow that has to be consumed for decomposition. So if we have a ruthenium catalyst, much higher, much more reactive, or as they call it, active. Activity of catalyst is used to measure basically the rate of reaction over the gas hourly space velocity. So ruthenium is going to be this by far much higher. Oh, and of course the activation energy, which is kilojoules per mole, is much lower for ruthenium. And so then we're going to go over, I think pretty soon, we're going to be talking about cesium as a promoter. Cesium increases the rate of reaction, but it also decreases the activation energy significantly, all the way down to, I think, 60 kilojoules per mole. So here, nitrogen, argon, and helium don't have an effect on fuel cell performance. Again, they don't have a direct effect on fuel cell performance, but they do reduce power output and efficiency because they essentially they serve as a blockage to hydrogen entering the membrane of the fuel cell. So okay. So the lithium X zeolite, without any special treatments, can decrease the NH3 concentration from 1,000 parts per billion to 0.1 parts per billion. Okay, this is very important because all of these reactors, regardless of whether they use a noble catalyst or a lower cost, a non-noble catalyst such as nickel, they don't reduce the residual NH3 concentration below around the lowest as we demonstrated there for the nickel reactor, let's say 5 parts per billion. Well, that's still in order of magnitude higher than 100 parts per billion. And so the absorbent is key. From the reactor to the fuel cell, we need that absorbent. Otherwise, the fuel cell will be poisoned. Now, again, that's assuming we use a PM fuel cell, not an alkaline fuel cell or a solid oxide fuel cell. Those fuel cells can be used directly with ammonia crackers without any issues. Okay, so the absorbent is very minimal as well for a 2,000 watt-hour operation. You're talking about 50 to 100 grams. Very minimal weight. It's not like we're going to have this very large absorbent required to carry on board. This is a cool little marketing thing that I made here. Dispense with high pressure micro ammonia cracker. This is what an ammonia cracker is going to look like. Essentially what you have is this module, and inside this module you have a series of plates that are stacked up upon each other, and between those plates you have a gap, and that gap allows for hot gases to flow through to provide the activation energy, and these catalyst channels are filled with using wetness impregnation. Again, a hydrogen tank, high pressure, 700 bar. You're talking about 1.5 inches of carbon fiber. And that's weight that you have to carry on board the vehicle for there's really no good reason to haul around all that weight when you can take advantage of chemistry. So some energy consumption estimates. We can calculate how much energy we need to crack our ammonia based on the total mass of metal that we're heating up. So that's going to be the catalyst channel. The rate of hydrogen and nitrogen flowing through, which has a heat capacity, which is going to absorb that heat that we're inputting into the reactor. And so we can calculate it comes to around 8 kilowatt hours per kilogram of hydrogen formed. So here we have 5 plus 2.6 plus 3. So about 10 divided by 33.3. 30%. Realistically, it's going to be less than that. It's going to be around 20%. And this was a very conservative estimate. And again, you can just calculate that based on we need to keep all of our catalyst channels at, let's say, 650 degrees. We know what the specific heat capacity of that particular metal is, and so we know how much energy is required to keep, let's say, 1 kilogram of that metal at 650 degrees. Then, of course, there's an additional requirement, and that is to establish how much heat is being carried away by the gases flowing through. So the hydrogen gas at high heat capacity is going to pull away a lot of heat, and so you have to take into account that heat loss from the absorption from the hydrogen, and so when you add that all up, you get around 20%. So let's keep going through. So for an electrical heater, and we haven't discussed this before, there's 2 methods to heat a catalyst. There's electrical heating and there is combustion heating. Electrical heating, of course, is going to require more energy, around 40%. Combustion heating, again, 20% is realistic. So nuclear absorbance, between 6 and 8% ammonia by weight, reduced from 2,500 parts per billion down to 1 part per billion. Okay. So 20% of the ammonia is consumed in the combustor. So they're actually burning ammonia rather than the the cracked hydrogen, or I should say, the hydrogen byproduct. So just more data on catalysts. We're going to go over the ruthenium catalysts pretty soon here. And people have studied all sorts of catalysts. There's one sodium amide catalyst that was studied. Just again, a plethora of catalysts that have been investigated. None of them perform very well except for ammonia. So here it was found that ammonia achieved 100% decomposition at 635 Kelvin. So, okay, so I suppose I'll go through this in a separate video, but this is what the picture's crappy, but this is an exhaust manifold. Now, the exhaust manifold contains these small modules, these containers. Inside the container, we have these channels. The exhaust gas flows through the passageways, heating up the catalyst, and you're going to be able to provide nearly 100% of the required energy to decompose the ammonia using the exhaust gases of internal combustion. This is proven. This was examined, and they found found not with this exact configuration actually, just a tubular catalyst, a tubular cracker, was used and placed on the exhaust manifold. Actually, I think further away from the exhaust manifold, and they were able to achieve 100% decomposition. The other thing is you don't need as higher temperature because we don't need to achieve these high conversion rates. If we're using a fuel cell, we want to provide as much of the conversion via the reactor as opposed to relying on the absorbent, because we're going to have to be replacing our absorbent all the time. So we run that reactor at very high temperature. If we're going to use a PM fuel cell, if we're using an internal combustion engine, we can reduce that temperature because we don't care if we have, let's say, 5% ammonia in our hydrogen gas. Ammonia will combust. In fact, ammonia can be combusted directly in internal combustion engines. The main issue, the main hindrance to using ammonia in internal combustion engine is actually ammonia emissions, which we call ammonia slip in an SCR, and that's regulated to, I think, 10 parts per million maximum. And so there's going to be some issues around having too much ammonia being emitted in urban areas. High entropy alloys of cobalt and molybdenum were also studied to be very very effective, but they're somewhat unproven. So more data on the high entropy alloy catalyst. I don't know much about the high entropy alloy catalyst. All I know is that you can't really buy them in the marketplace right now. So in the future we might be using high entropy alloys. There's a lot of research around high entropy alloys, but not really much is known. Okay, ruthenium price, from what I understand, is about $8,000 a kilogram. So 165 an ounce. I don't really feel like converting that right now. The reserves of ruthenium are 11,000 tons, in case anybody's interested. And I don't think ammonia cracking as an energy system is going to ever become large enough to even make a dent in the total supplies of ruthenium, because we're going to get to the most important number soon, and that's the amount of ruthenium catalyst in grams required to crack 1 kilogram of hydrogen per hour. It's very negligible. The catalyst by mass is only about 8% ruthenium. In fact, if you go above about 10%, you're not seeing an increase in reactivity. It starts leveling off, so there's diminishing returns. So if you go from 4 to 8%, you have a significant increase, but if you go above 8%, it doesn't increase very much. And I think I'm going to get to those numbers soon. Here is the example of a cracker channel plate. So you have this plate, which could be made of various metal alloys, ideally those with a high thermal conductivity. And the grooves are lined, again, using wetness impregnation with the catalyst. And then those are stacked upon each other, and you have a gap between the catalyst plates, which permits the flow of a gas, a hot gas that could be combusted, this hot air with the heat provided by burning hydrogen. So 11,300 tons of ruthenium reserves. So a lot of people are, and the reason I brought up the ruthenium reserves is because if you read papers about ammonia decomposition, a lot of papers are studying alternative catalysts, non-nova catalysts, and they're citing the short supply of ruthenium as a potential barrier to implementing a widespread ammonia economy, and so for that reason, it's considered a viable potential large-scale energy system, and therefore we need to ensure that supplies are sufficient, but they are. It's not a limiting factor. So pretty soon we're going to go over the rate of reaction versus the loading, the catalyst loading. Okay, so these are unrelated data here, not related to reactors, related to engines. Okay, so here again, sort of the structure of this discussion is a bit random, kind of going back and forth to unrelated subjects. But the general idea is hydrogen, high pressure hydrogen versus ammonia. And then if we're going to talk about ammonia, we're going to talk about the necessary technology required to implement an ammonia hydrogen propulsion system, energy system, and so in that comparison, we have to discuss safety, and we also have to discuss cost and efficiency and energy density being the most important metric. But regarding safety, you can see here 50 accidents involving hydrogen fueling stations have been reported, right? So and this, Japan's been implementing an ammonia economy hydrogen economy for a long time. So when people come from the hydrogen community, and I'll quote Greg Bizzini, I think is his name, and he said, the hydrogen guys really didn't like what was at the time a small community of people advocating ammonia. I think this was in the 1990s. So there has been a community promoting ammonia for a long time. Ammonia Energy Association. These guys are basically saying, look, you want a low carbon energy system. Maybe you should kind of broaden your scope, right, and get out of this kind of having blinders on and looking at only fuel cells and batteries or on the table. There do exist other energy systems. In the second video, we'll talk about hydrogen. And what I ask you is like, we're developing these systems because you want to reduce carbon emissions, right? There's no other reason why you want to use anything but a 2019 BMW spark ignited gasoline engine, right? It's affordable, it's high performance, it's quiet, and it's relatively clean, excluding CO2. But it releases carbon dioxide, right? You can only tune your engine so much, you're not going to be able to get carbon dioxide eliminated. It's a fundamental chemistry of the fuel. So the only reason you want to use these alternative energy systems to reduce carbon dioxide emissions out, you should probably consider this fact, that there may be some consequences to using these alternative types of energy systems. Batteries, if you charge a battery at a very, very high rate, you risk overheating that battery and having a fire break out. Okay, that's just a fact. You can argue against it all you want, but it's a fact. So all of these energy systems are going to have risks associated with them. They're going to have a certain degree of risk built in. The question is, assuming holding that risk constant, which system is most competitive and most viable? And the argument that they've been making, and I'm making in this video, is ammonia is going to be a lot more viable, assuming the risk is relatively similar to what is currently being advocated. So, anhydrous ammonia and carbon steel. No appreciable difficulties with steel equipment used for handling, storing ammonia have been experienced in the chemical and refrigeration industries, right? That's one thing we should remember is ammonia is right now being circulated in some building somewhere, in a industrial building, a supermarket, whatever. I'm not an expert on the refrigeration system, but it's being used in close proximity to humans inhabiting these buildings. Okay, so on the other hand, hydrogen, I don't think, it's used for cooling large turbo generators, but humans are typically not in close proximity to those systems. Aluminum alloys, 1100, 3003, 5052, and 6063 showed only mild etching after 1 year of exposure to liquid ammonia. Very little corrosive effect on most aluminum alloys. Okay, so on the other hand, hydrogen, gaseous hydrogen at high pressure. So high pressure exacerbates the tendency for embrittlement to occur. And embrittlement is essentially the hydrogen atoms being so small, they permeate through the crystalline structure of the metal, and they form internal pockets, and those internal pockets expand, and they fracture the metal. That's an oversimplification of embrittlement, but that's the main challenge. And sometimes that hydrogen can bond with carbon within the metal and form pockets of methane. But regardless, the idea embrittlement is fundamentally the fact that the hydrogen atom is so small and it's going to permeate through just about every compound. Whereas ammonia does not appear to cause serious embrittlement. Okay, so H2 embrittlement is a process which H2 introduced into a metallic component causes the structure to crack. So H2 molecules dissociate into atomic hydrogen, so monatomic hydrogen. H2 atoms are unstable and will reassociate immediately to a molecular form if they enter a void in the metallic structure, and that's where methane tends to form. So essentially, it's atomic hydrogen. That's something that I had forgotten. I had not been aware that it broke down into atomic hydrogen. But okay, so ammonia is easier to handle than hydrogen because it doesn't require high pressure. Well, we know that's significant money and reducing risk of explosion. Hydrogen embrittlement. Farming and refrigeration industries have been handling ammonia for decades. Okay. We know all this already, but just kind of reiterating it because people are really stubborn. Okay, so this is back to catalysts, 8 to 40 times more active than other metals. And again, I apologize for this kind of random nature of this, but I'm too lazy to put it together in a slide, so ammonia versus hydrogen storage costs. H3 filling station 70,000, H2 2.5 million, right? So that's 2.5 million for these fueling stations. And again, you can imagine, 700 bar is an insane amount of pressure. Every flow regulator, every valve, every sensor is going to have to accommodate that high pressure, and it's going to have to be engineered, incredibly overbuilt to achieve a sufficient safety factor. So here's an interesting illustration of the different risks associated with the 3 types of fuels, and that's gasoline, ammonia, and LPG. This was performed by an independent consulting company, and they've established that ammonia is actually it's more dangerous than gasoline, but it's significantly safer than LPG, and we could assume LPG would be comparable to hydrogen. I would say hydrogen would probably be a bit more dangerous. So as you can see, your hazard radius is significantly greater for LPG than ammonia. This is another important factor, that a fuel used to power a vehicle does not contribute significantly to the fatality rate of motor vehicle accidents. And of course, there's an argument you can make for batteries or hydrogen. There's a lot of disagreement as to whether batteries are safer or more dangerous than gasoline. It's very politicized, and then people against battery cars argue that there's a safety risk there that's not being appreciated by the battery advocates. And I don't have the data, so I'm not going to be able to speculate. But so refueling station contributes approximately $7 per kilogram alone, just a refueling station. And as we know, $13 to $15 a kilogram H2 for at the dispenser in California. We have to understand that these are very mature technologies. I mean, you're talking about valves and metallic components and hoses and pipes and dispensers and nozzles, regulators and sensors. I mean, these types of systems, compressors we can include as well. These systems are sold at basically production costs. There's not a lot of profit involved, and you could say, well, what about the manufacturing volume? Because these systems are manufactured at very small volumes. Well, yes, but a lot of these systems are interchangeable. So if you're making hydrogen compressors, you could also be making helium compressors. And I think factories have been making probably the same amount of helium compressors. Helium compressors have probably been pretty steady in their production volumes over recent history. Maybe helium compressors, any kind of gaseous compressor for that matter. But it's just an example. So I don't think that it's reasonable to argue that you're going to be able to significantly reduce the cost of these, what are entirely mechanical systems, with production volume. I think this argument that, we just increase production volume, costs come down, that is often exaggerated by proponents of a particular technology. And they're often getting confused with, they're often extrapolating from totally different industries, such as computing and information technology, software, whatever, and they apply that to things like electrochemical systems, like batteries, and it's true that batteries have come down in cost a lot, but that's mainly because their lithium-ion batteries are not a mature technology. They were in the developmental stages, and advancements in manufacturing took place that are not likely to occur in industry such as manufacturing compressors, where a lot of this cost lies. So I don't think it's fair to compare these totally different kind of sectors, Okay, so hydrogen compressors, as you can see, you can see just from this number, the power consumption is very high per kilogram of hydrogen. Okay, so capacity 10 cubic meters, is 0.82 kilograms. 5.5 divided by 0.8 is about 7 kilowatt hours per kilogram, and that's to 300 bar. So 700 bar, it's not double, but it's probably 50% more. So power required to compress is not linear. It's not intuitive. So at higher pressures, power consumption is reduced. Data on LPG accidents. A solid oxide fuel cell with a steam reformer. It's not projected that solid oxide fuel cells would be viable for transportation applications, primarily because of their poor cyclic operation capability. They are not able to readily be adjusted in their output due to the high temperature, and if you cycle them on and off, you're going to impose a great deal of thermal stress and reduce the lifespan. So solid oxide fuel cells are not going to be competitive for transportation, but for stationary applications such as a power generator, it might make a lot of sense to have a solid oxide fuel cell. Reform ammonia. You have plenty of heat from the anode gas to fuel the reaction. So fuel cells increase in power output at higher pressures. That makes sense. New fuel cells are being designed to run at higher pressures. That's one potential issue that needs to be addressed with ammonia reaction, is that for ammonia decomposition, you want to be at the lowest pressure possible. So the rate of reaction decreases at higher pressure. The highest conversion rates are found at very low pressures. Now, we want sufficient pressure to pass through our membrane separator, and then we might want higher pressure for the fuel cell. Now, these are not high pressures. I mean, you can the membrane separators typically operate at slightly under 1 MPa. That's obviously significantly higher than what you want for decomposition, which ideally you'd want to be below atmospheric pressure, but typically it's going to occur at atmospheric pressure. At 1 MPa, rate of reaction is going to decrease significantly, and so we want to avoid running the reactor at high pressures. Again, we're going to get data on that as I scroll through, but you will have to compress the reform gas prior to going into the membrane separator and the fuel cell. Here is a microchannel ammonia decomposition reactor. Most of these are built by Fraunhofer in Germany. I don't know of any other companies making these. They're very specialized components that are not readily manufactured. Here is the channel groove. As you can see, you have the catalyst and the channel. And here are the dimensions, so obviously very, very small. What would ammonia tanks look like on the vehicle? Here is an illustration. I think this is for, I don't remember the range, but reasonably good range, in excess of 500 miles. Minimal volume occupied compared to 700 bar. I don't have a comparison to 700 bar, but the density difference is, well, it's 120 versus 30, because you have to account for the thickness of the tank, so it's around 3 to 3.5 times the difference. So this volume would be, let's be conservative and just assume 3 times more for hydrogen. Okay, so if we want to combust ammonia in an internal combustion engine, we're going to have to deal with the issue of about 60 parts per million ammonia emissions. So that's an issue that's going to need to be solved. Some kind of scrubber, some kind of absorbent material possibly could be installed in the exhaust system. I'm not sure what exactly would be required, but it's not attractive to combust ammonia in its pure form. Using a reactor, we could crack, let's say, 80%. and that 20% ammonia is going to be nearly completely combusted because we have so much heat, so much energy from that hydrogen that's going to overwhelm that ammonia fraction, and the residual concentration is likely to be much, much smaller than if we burn pure ammonia. In some cases, they didn't find any NH3 concentration in the exhaust gases. If you get the air-fuel ratio right, you get the equivalence ratio right, if you have a high combustion temperatures, I imagine you could probably reduce it to very minimal levels. So what does the combustion look like? This is 60% NH3 and H2, and 34% NH3 and CH4. Fuel oil. Right, as you know, makes sense. It's much slower flame. Here's a membrane separator. Why we talked about membrane separators again before we get into our fuel cell. Before we pass the gases into our fuel cell, we want to separate as much nitrogen as possible. And one of these small membrane separators that I pictured earlier can provide sufficient separation to get most of that nitrogen out and not impair the efficiency of the fuel cell. So again, the way it works is that you have gases. Smaller gases are going to permeate through the perimeter of the tube, and larger gases are going to continue flowing through the tube. This is one of the most important pieces of data. So it shows the cesium loading and the rate of reaction. So rate of reaction increases sharply with higher cesium loadings. Now, then if we move to ruthenium loading, we don't get nearly as sharp an increase in the rate of reaction. So we can have a 4% loading and we're 70% as much reaction. Our reaction is 70% as much as 10% loading. So we want a medium ruthenium loading and a higher cesium loading. And cesium is a lot more expensive than ruthenium. The reserves are much, much larger. Cesium reserves are very large, 350,000 metric tons, and 24% weight is cesium. So we got plenty. Now, this is very interesting, the way that we're not getting a big increase in the rate of reaction for higher ruthenium loading. So most of the reactors I saw were 8% ruthenium loadings. So here is a comparison of a nickel versus ruthenium cesium catalyst reactor. And so you can see the difference in the production rate. Very, very significant difference. So around 10 times higher for the ruthenium. Okay, so these are very important numbers. And then I'll go over the longevity of the catalyst. So 6-hour continuous tests, approximately 280 hours of experimental work. Found minimal deactivation during this period. So 150 hours plus another 750 hours. Reactor had endured 750 hours of daily startup shutdown operation. Shows that the reactor operated with good long-term stability over the recommended operating conditions. A washcoat stability could be checked forcing open the weld on the laser welded reactor, but this wouldn't tell us during the reactor. Okay, well, the point is, okay, 900 hours, so let's say 1,000 hours, minimal deactivation. Okay, 1,000 hours is a very significant period of time for this type of high temperature reactor. Okay, so this is an important number, 750 hours, but we'll go back to where we were. Okay, so another important point, microchannel reactors have a substantially smaller footprint and enhance heat and mass transfer rates 50 to 100 times by virtue of their small channels, which essentially it's about the surface to volume ratio. If you decrease the diameter of the channel to these very minute sizes, you will enable very, very high rates of heat transfer. Okay, so we're going to discuss the details of the cracker now. Cracker uses 4% weight ruthenium, 20% weight cesium. Now I've removed this carbon nanotube and replaced with aluminum oxide because the stability of the carbon nanotube is poor. I don't know if I think I forgot to show that. Cracker specifications. Okay, Chiuta published a lot of work on crackers. Activation energy could be as low as 49 kilojoules per mole. Probably going to be more around 80. I've upped these numbers. Again, it really varies a lot, but the most important number is the amount of ruthenium needed. So I estimate around $1,000 to $2,000 per kilogram hour of capacity at high production volumes. Okay, so ruthenium required for 1 kilogram of hydrogen formed 1 gram. Okay, and cesium 5 grams. So gravimetric density, the cracker only weighs half a kilogram per kilogram of hydrogen produced per hour. The density is only half a liter per kilogram of hydrogen produced per hour, and the energy consumption is probably 6 kilowatt hours per kilogram, although that's going to vary a lot depending on the temperature. And from the exhaust gas, we can get 100% of the energy. So the price of ruthenium is $8,000 a kilogram. Price of cesium is $30,000 a kilogram. Now, so this is the exact catalyst that we would likely be using, Acta Hypermech 1010, specifically designed for ammonia decomposition. A lot of papers published on this catalyst. Very high reactivity. I think it's cesium promoted. And so this is the ideal catalyst that you would use. Okay, so the price, they have to distribute the ruthenium on the aluminum oxide. That adds cost, but the actual cost of the raw materials is very small. I mean, if you're talking about talking about 1 gram, right? 8,000. $8 a gram. That's $8 to crack 1 kilogram of hydrogen per hour. Now you assume, well, it's going to be a lot higher than that because you're going to have to place the ruthenium on the aluminum oxide, right? You're going to have to mix the ruthenium with the support, right? A catalyst it has to be supported. But regardless, if you're looking at if you assume that the cost, let's say, for the raw material represents 10% of the cost of the final catalyst product, then we can assume it's about $100 per gram. And so that's about $100 just for the catalyst for 1 kilogram of capacity. So if you have a 10 kilogram capacity cracker, we have $1,000. And then we have the cost of manufacturing and impregnating the catalyst, or manufacturing the actual catalyst, the cracker module, the plates, the channels, and then impregnating it. So, if we're assuming $2,000 per kilogram capacity, right? The raw material cost is only realistically like 10% of that cost, right? So the point is that there's no reason why this couldn't be very affordable, right? And this number here, total catalyst mass per kilogram hour, H2 reformed, 25 grams, that's simply based on the numbers that I have. Take the data for the microchannel ruthenium reactor, which we're going to find shortly. So, 3,000 milligrams, and I just computed the flow rate. So H2 production rate, 9 nominal liters per minute. So yeah, you just go by that data and compute it. HISA infrastructure, they're the ones that research these ammonia reactors, and they manufactured them from, they imported the reactor from Fraunhofer microstructured reactor technology. Fraunhofer manufactures these, and they wash-coated the catalyst. They impregnated the catalyst. They manufactured the entire reactor, and these guys in South Africa studied it. The reason I think they're doing it in South Africa is because they have a lot of ruthenium. So they have like most of the ruthenium reserves are in South Africa. So anyway, the most important numbers, the most important data is going to be the cost of manufacturing that reactor and its longevity. It was shown 1,000 hours is realistic, and that's they didn't push it any further than 1,000 hours. At least 1,000 hours. Minimal cost, $2,000 a kilogram capacity, and the potential to either harness exhaust energy or have a dedicated combustor module providing the heat for fuel cells. Because you don't have any heat from a PM fuel cell, right? It's a low temperature fuel cell. And the rationale is because, well, it's low pressure, it's liquid, it's easier to handle, et cetera, et cetera. Well, it's liquid under storage, but it's a gas under atmospheric conditions. But you pressurize it to 10 bar, whatever, it's a liquid. And 10 bar is better than 700 bar. So those numbers alone should convince you that ammonia is the only viable way to achieve a fuel cell infrastructure. It's the only viable way to achieve a fuel cell economy if you want to do that. So I guess I'll leave it off right here and just encourage people to study these microstructured reactors, encourage people to study the catalyst, whatever. Well, I think it's probably futile to keep trying to research these alternative catalysts because they all show up the same results. They all show the same results, and that's poor activity and higher temperature required. And so, ruthenium with cesium promoted microstructured reactors are going to offer a very powerful package to enable to readily enable the convenient decomposition of ammonia on board a mobile system. For stationary applications, you probably want to use a solid oxide fuel cell, and since you don't need the higher conversion rates because solid oxide fuel cells aren't sensitive to ammonia the way PM, you could use a nickel reactor, right? So stationary applications use nickel, and there's companies that do this already, like the company in Israel, or I'm trying to think of their name. Gencell. So they're using alkaline fuel cells. So we think the PEM fuel cell, the microstructure ruthenium reactor, and no one's doing that. I want to emphasize, no one is manufacturing turnkey module with, and this is what we're offering. If you go to GrabCAD and you put fuel cell, what we're focusing on making is this system right here. Integrated package with tanks, purifier, PM module, cooler, and cracker. Now, cooler, why would you need a cooler? Well, you can't flow 600-degree gas into a fuel cell, a PM fuel cell. You're going to damage the membrane. You have to cool it down as it exits the cracker. It's a very high temperature. You need to cool it down with basically an EGR cooler. Not an issue at all. So, I say here, okay, moving beyond cell towers. Cell towers are the only application currently for ammonia energy. Okay, so we have a small combustor. We're not going to get NOx emissions because we can run it stoichiometric of a small little three-way catalytic converter. And we're hardly burning any hydrogen anyway. Reactors from Fraunhofer, stability of catalyst over 99% over 1,000 hours. Nanopore insulation, we can encapsulate the reactor in this nanopore vacuum channel insulation to minimize heat loss. The high temperature gas consisting of 75% hydrogen, 25% nitrogen is sent to the liquid cooled heat exchanger, similar to an EGR cooler. Temperature is reduced to 80 Celsius at this point. The cool gas is sent to an acid impregnated carbon base absorbent. That's manufactured by Calgon Carbon Ammon Absorb. That's hard to pronounce. To purify below 10 parts per billion. Okay, we remove our nitrogen until we only have 1% nitrogen concentration using polymeric membrane. The now highly purified cool gas stream can enter the proton exchange membrane fuel cell. 25% hydrogen is required to provide the heat to form the ammonia. Net efficiency is 45%, and we have our puncture-resistant, ultra-high molecular weight polyethylene tank. And this is all to scale, so it's just based on, this is not just a visual model, it's based on real engineering analysis. What's interesting is look at how much smaller the cracker module is compared to the fuel cell. The cracker module is where my mouse is right here, if you can see it. I hope I'm recording my mouse. Yep, I am. Cracker module is quite small. This is a cooler module, and the PM module right here, and the polymeric membrane. And our tanks, we went with, I think, 3/4 of an inch of ultra-high molecular weight polyethylene. And again, the rationale behind that is that it was involved in a collision. A piece of metal being hurled at a high velocity would potentially puncture through the thin-walled aluminum tank. With the ultra-high molecular weight polyethylene, it would absorb that energy. It would probably permanently deform the tank, the aluminum substructure of the tank, but the polyethylene would prevent it from fracturing and reduce the risk of releasing ammonia into. So you need, for it to be life-threatening after 30 minutes of 2,500 parts per million. Now, 2,500 parts per million is a very high concentration. 5,000 to 10,000 for less than 10 minutes. No data on fatality, but life-threatening after 30 minutes. It should be noted that several people survived after being exposed to concentration in the order of 70,000 parts per million. So yeah, this is, if you want the data about the concentration required for it being life-threatening, it's very high. It is heavier than air, right? Ammonia is ambient density. Ammonia is lighter than air, so it's going to immediately rise, and therefore it's not going to linger in a puddle on the ground after spillage. So that's one major advantage to take into consideration. So is hydrogen. Propane, on the other hand, is heavier than air, so it will linger and potentially pose a bigger explosive hazard. Now, you're comparing a different danger, again, as we were talking about in the beginning of this video, toxicity versus fire and explosion hazards. But in the end, it's probably a similar risk, and if we go by that diagram that we showed, regarding the hazard radius, it's actually safer than LPG. And if you go to OSHA accident database, put propane, go through the list, compile the number of accidents. I did it. I forgot the number. I can probably find it in my history. But it was, if you take total number of accidents for propane, tons of propane consumed every year, total number of accidents for ammonia, and then you just take the total number of accidents divided by the number of years, and then get that per year number, and then compare that to last year's total consumption. And that's what I did. And so ammonia was less dangerous than propane. And again, I can't compare to hydrogen because hydrogen includes hydrogen sulfide, and I actually couldn't get that many includes hydrogen sulfide and possibly it's too time consuming to separate. So but yeah, so the final statement is that I don't have reason to believe that it poses a significant safety hazard. Considering the benefits of zero carbon fuel having basically storage properties that are similar to propane and very low cost at that, it would be foolish to ignore this very attractive energy source in the future low carbon mobility landscape. And not just mobility, power generation, marine applications, I guess falls within mobility. But when we're talking about ammonia, I'm not talking about passenger cars as a prime application. I'm talking about commercial vehicles, heavy equipment, off-road equipment, generators, marine. These are big segments of transportation that account for a significant portion of carbon emissions. So you can't just look at passenger cars. You have to look at these other segments. And any kind of commercial segment, you can deal with that. If you perceive the risk to be higher, we can better deal with that and cope with that by taking necessary measures such as having PPE. You say, well, that's crazy. Why would I want a fuel that requires PPE? Well, natural gas trucks, liquid natural gas trucks, which are widely used in China, require a face shield and gloves to fuel up the vehicle because you could burn yourself through the very cold temperature of the cryogenic gas. So it's actually technically not burning, but if you're exposed, you immediately freeze your skin. Actually, I should say, somewhat comparable to burning. So liquid natural gas trucks require the use of PPE to prevent against freezing your skin by coming into contact with small droplets of cryogenic gas. So in these commercial segments, we can better cope with these challenges that fuel may pose. And in commercial segments, energy density is more important. Being able to fill up the tanks faster, we can do that with ammonia. I should mention that the flow rates can be much higher because 700 bar, the flexible hoses, the flow rates are pretty slow. So it actually takes a lot longer to fill up a hydrogen bus or hydrogen truck than a diesel truck. With ammonia, it's closer to liquid fuels in terms of fill-up time, and again, that's important. For storage density, it's just beautiful. As for energy density, gravimetric, weight, kilowatts per kilogram, it's very competitive. It's from what I gather the highest non-carbon containing fuel. So significantly higher than batteries, an order of magnitude higher than batteries, and twice that of 700 bar hydrogen. And so the thing to be noted with hydrogen is that energy density doesn't increase gravimetric with storage density with pressure. So 700 bar is about 5.6%, 300 bar is about 5%. So it's all around the same. It's very poor. So we got to have a higher gravimetric energy density. We need better volumetric energy density. We need faster fuel up time. We need lower cost, and we need low cost infrastructure. And we need to be able to use the existing infrastructure, and only ammonia can provide that. So I think it's silly to ignore it, considering the imperative, the tremendous need to develop a low carbon propulsion fuel for especially these heavy duty segments. But I'll leave it at that.